Hi guys, so we're continuing our coverage of chapter 2. In this video, we'll be looking at the sample regression function. So the sample regression function, the relationship between the sample regression function and the population regression function is similar to the relationship between estimators and parameters that we saw in Appendix A. So we had estimators for the mean, variance, etc. of distribution characteristics, and the sample regression function is just the estimators or the estimate of the population regression model. So like in the case with Appendix A, when we deal with the sample regression function, we are using sample data, and we are using the sample data to estimate the regression parameters. And as you will recall was the case with Appendix A and the distribution characteristics, when we draw different samples of a given set of data and estimate regression models based on those samples, we'll get different values for our parameter estimates each time we draw a different sample. Now, ideally, we would draw a sample and estimate regression parameters in such a way that they are as close as possible to the actual parameter values from the population. But of course, it's hard to know how close we are given that we never observe the true values of the population parameters. But in Chapter 3, we'll introduce a technique that at least allows us to try and minimize errors when we estimate a regression model. Okay, so there's just a note on notation. So when we talk about the population regression function, or PRF, we specify it as given over here. When we talk about the sample regression function, we now include a hat on the y, the outcome variable, as well as the parameter estimates. So beta 1 and beta 2 over here are population parameters. Beta hat 1 and beta hat 2 are sample estimators, or just estimators of parameters, or more specifically, estimates of parameters. As usual, the stochastic specification merely includes the U term at the end. Note here that the SRF should have a hat over the Y variable. That is because the Y variable is being estimated in this model. The X variable does not get estimated, the Y variable is estimated. So that should have a hat in this SRF specification at the bottom here. So this slide just highlights the fact that drawing different samples can give you different sample regression models. So here you have two models labeled SRF1 and SRF2, and each of these models are drawn using different samples of data. So SRF1 is drawn using the X's as the data points, whereas SRF2 is drawn using the dots as the data points. And as you can observe, there are different slopes. They're both upward sloping, but they have different values for both their slope as well as their intercept parameters. Now there's a question being asked over here. What is the better one? Well, we don't know. Unless we have a PRF that we can compare to, we won't know which SRF is closer to the PRF. And usually, we don't have access to the PRF, so we never know. As usual, best is just to sample as much data as possible. Alright, so what's the difference between the stochastic error term and the estimated residual, which is the term for U over here? I should have made that clear. We call this the residual in the SRF situation, whereas for PRF, we call this the error term. Just a bit of nomenclature to be aware of. So what is the difference between those two things? Well, the error term is the deviation between the different values for y and the expected value of y given specific values of x, whereas the error term will be the difference between all the observed y values and the estimated y values. So recall that this thing is simply an estimate of that thing over there. But in both instances, in principle, what these what this residual and this error term are doing is accounting for the variation in y that is not due to x. So this is just a graphical illustration of the difference between ui and u hat I. So ui is given over here, which is the difference between some data point, some observed y value, and the PRF. Again, we never observe this. And then u hat I is the difference between the same yi, the same data point, and the estimated sample regression function. Okay, so we said at the beginning that we are dealing with linear models. And this is an important thing to understand, what we mean by linearity in this case. So you can distinguish between linearity in variables and linearity in parameters. We are interested in the latter when we talk about linearity. We mean linearity in parameters. Linearity in variables implies that y and x are strictly linearly related. Therefore, any specification of the regression model must look like this. Forgive the poor betas over there. You cannot have any other specification for a regression model if we subscribe to this principle over here. But what we mean by linearity is that the regression model must be linear in parameters. The yi must be linearly related to beta 1 and beta 2. And in short, what that implies is that these parameters appear in the regression model with the power of 1 only. Now, what that means in practice is that x and y can be related in non-linear ways. So here you have a panel of 3 graphs. In the first one, you have a quadratic relationship between y and x. And although x and y are not linearly related, all the betas appear to the power of 1. So the betas are linearly related to the y. Now over here, in the next panel, we have an exponential function. Now, as it's specified over here, the betas are not linearly related to y. However, we can do a transformation on this function. So if we take the natural log of both sides of this function, we end up with ln y equals beta 1 plus beta 2 x. Now, these are linearly related to the left side of the equation. So sometimes a model specification can be transformed in such a way that it can be made linear in the parameters. The last specification on the slide just takes the quadratic to the next level. So here you have a cubic relationship, a polynomial, third order polynomial relationship between y and x. And again, all of the betas are expressed to the power of 1, and these are therefore all linearly related to y. So we can use regression to estimate such a model. Now, given our previous discussion, we can ask ourselves whether any of these models are linear in the context of regression models. So if we look at A, we notice that both beta 1 and beta 2 are to the power of 1. And so we can conclude that yes, this is a linear model, linear in the parameters that is. And likewise with B, we have the same situation. Both beta 1 and beta 2 are linearly related to y. And we have the same situation for C. However, when it comes to D, we notice that here we have the natural log of beta 1 and the natural log of, well, it turns out that beta 2 is in fact linearly related. However, we have the natural log of beta 1, therefore we cannot say that this model is linear in the parameters. E, on the other hand, once again is linear in both beta 1 and beta 2. And here we can do the same exercise. Now, here we have some specifications where transformations might make the models linear. So none of these models are linear in beta 1 and beta 2, except for C, right? So model C in its original state is linear. Now let's look at A. Well, we've seen this one before, and we said that should we take the natural log of both sides, we end up with natural log of y equals beta 1 plus beta 2 xi plus ui. And this model is linear. So under transformation, A becomes linear in parameters. You can similarly show that B also becomes linear in the parameters under transformation. There's a couple of more algebraic steps than in A to get there, but again you can show that this becomes linear. When it comes to D and E, however, neither of these can be transformed in such a way that will make them linear in both parameters beta 1 and beta 2. So these cannot be transformed so as to be linear. And this slide shows you some more examples of models that are not linear as stated. However, they can be transformed so as to be linear. And when we have a situation like that, when you have a model that is, as explicitly stated, nonlinear but can be transformed so as to be linear, we say that they are inherently linear. So all of these models are inherently linear in the parameters, or intrinsically might be a better way of stating it. Alright, so there's a couple of exercises remaining for you to do on the slides, but for now I think we'll leave it at that. See you in the next video.